How did the universe get to be filled with structures, ranging up from galaxies to superclusters, with a delicate pattern in three-dimensional space? We think the single force of gravity caused this to occur over 10 billion years. The best insight on how this happens now comes from supercomputer simulations. Pure theory gives us some ideas, but the details are often fleshed out in a computer simulation. The power of the computers allows us to put a billion or more particles into the simulation and see how they would interact by gravity over cosmic time. We're making a miniature universe in a computer, we're speeding up time, and we're calculating the gravity between each particle and every other particle. As you can see, this will be trillions of calculations every time the particles move, and so this is very intensive of computation. Really, supercomputers were the only way to do it until about 10 years ago, but now desktop clusters are able to produce the same results. These simulations, in a virtual space inside the computer, need the key ingredient of dark matter to produce anything like what we see in the real universe. Simulators use various numerical tricks so that the calculations can be done fairly quickly. For example, since gravity is an inverse square law, it's not necessary to calculate the gravity of every particle on every other particle in the simulation. For a billion particles, that would be a billion squared calculations every time there was a time step. In practice, you can calculate the gravity from the nearest particles and then use averaging for the more distant particles. These various tricks and techniques have matured a lot in the last 10 or 15 years, such that astronomers have quite detailed views of how structure formed both within galaxies and on the very largest scales. The general properties of structure formation in the universe stem from the properties of dark matter. Astronomers talk about dark matter as being cold dark matter, where the word cold refers to the speed of those particles before the first structures formed early in the universe. Cold means that the particles were subrelativistic. With this property of dark matter, what happens is that the smallest structures form first, and they grow by merging. This is called hierarchical structure formation. So we should expect to see the largest galaxies having formed relatively recently. The story can't be quite this simple, because there are some massive and large galaxies whose ages seem quite substantial. But we see structure formation happening this way. We know the Milky Way is devouring dwarf galaxies right now, and we can see galaxy mergers taking place. The structure formation process is nonlinear, because as gravity draws gas into a smaller region, the collapse accelerates in a form of gravitational freefall. And so once structural formation begins, it proceeds more and more rapidly. In a computer simulation using dark matter, which is the key to how structures form, since it dominates normal material, the particles are placed in a three-dimensional volume. The expansion of the universe which is occurring is factored out because it will be hard to watch the volume growing, but it is part of the calculations. In this simulation, we watch the cube rotating so we can get a sense of the three-dimensional structures formed. And we follow it from a high redshift, 100 million years after the Big Bang, to the present day, redshift 0. Redshift is denoted by Z in cosmology. One of the most impressive simulations in the last decade was called the Millennium simulation, which included 10 billion particles, the largest simulation ever attempted. It simulates the entire visible universe, and zooming in through this simulation, we see the phenomenal level of detail that can be attained with modern supercomputers. Remember, in this simulation, we're only looking at dark matter. The visible matter is like the froth on the tops of the crests of the waves you might see on an ocean surface. The Millennium simulation spans 3 gigaparsecs, or over 10 billion light years, a substantial fraction of the volume of the visible universe. To see in more detail how hierarchical structure formation works, let's look at a simulation of a cluster of galaxies forming over cosmic time. We see the rapid motion of the galaxies driven by the invisible dark matter and their slow merger and coalescence as lighter and lighter galaxies are drawn into the general volume. After 10 billion years, a large central galaxy is formed, and it has a shroud of lighter galaxies, still moving in rapid motions because the overall cluster mass has grown. We can even look at smaller scales and simulate what happens when a galaxy like the Milky Way formed. We think this might be the history of our own galaxy, and we have some archaeological relics in the stars of our own galaxy to tell us that this idea is not entirely wrong, including the fact that our Milky Way is currently devouring several dwarf galaxies. In general, the galaxy formed fairly early. The oldest stars in the Milky Way are not much younger than the universe itself. The bulge stars form quickly, and then material in the disk accretes more slowly, and star formation continues through most of cosmic time. The formation of spiral density waves, evanescent patterns that trace the spiral arms, is the most delicate feature of a spiral galaxy, and is explained by simulations as well as the overall structure. We can put all this together in an animation that takes us from our terrestrial environment out through the different scales of the universe, the nearby galaxies, the clusters and voids and filaments, out to the most distant landmarks of galaxy evolution, the quasars and active galaxies, and finally beyond to the limits of observation, the microwave background, signature of the Big Bang itself. Structure formation in the universe is gravity, driven primarily by dark matter, the unseen component of our universe that dwarfs normal matter, made of the atoms in our bodies and stars and planets. Supercomputers are now used to simulate everything from the entire visible universe and structures on the largest scale to the formation of a galaxy like the Milky Way, where we can see the details of how the spiral arms form and how the galaxy is grown by eating dwarfs over a period of billions of years. These computer simulations only have veracity with observations when dark matter is included.